All right, so the plan for today is we'll finish off this existence thing that I want to talk about, then we'll take a short break again, and then we'll start talking about uniqueness. So that's what's coming up. Great. So maybe recall, like yesterday when we were talking about these existence questions, we said that there were, obviously there are constructions and then there are obstructions. And then I said that I can't possibly tell you about smooth obstructions because those are too hard, but you'll learn them from these other mini courses. But we saw a topological obstruction. We also saw a smooth construction. That was these surfaces in CP2 that we constructed by hand. But the last thing that I owed you was some sort of topological construction. So that's my favorite thing that I wanted to talk to you about. As topological constructions go, there's this very central theorem called the disk embedding theorem. That's like the key thing that powers basically every topological construction that we know how to do. So let me state a version of the theorem, and then we'll talk a little bit about like generalizations and applications and things like that. So here's the disk embedding theorem. Big enough? Yesterday I was shrinking, but I'll try to be bigger again. And this is, the initial work, there's a very central component due to Kassin from the 1970s, but the main thing that I'm writing down is due to Freedman and Quinn. Freedman and Quinn, let's say 80s. And as you can imagine, I'm going to try to embed disks. That's what this theorem will do. And it's going to be in some purely topological four manifold. For the moment, let's assume that the fundamental group is trivial. That's not, we'll talk more about that fundamental group condition in a bit. So I'm going to try to embed something. I need an input. The input is going to be a map coming from a disk. So assume we have two things. So the first thing is going to be some map little f. That's going to be from D2 into my four manifold. And I'm going to assume that the boundary is already embedded. Let's say locally flat. This symbol is supposed to mean generic immersion, but you can think of it as just a continuous map, and that's really fine. If this is a smooth manifold, you know what a generic immersion means. It's a two-dimensional thing mapping into a four-dimensional space. So at most, you can assume that there are generic double point singularities, sort of like that little loop over there. Okay. And in fact, over here, let me draw what we start off with. So here's boundary M, here's M, and I'm going to start off with a map of a disk that looks like this. So this is F. The theorem will say in the end that I can change F by a homotopy rel boundary to an embedded disk. Turns out you can't always do this with just an F. And you should think about, like, for example, not all knots are slice. And therefore, you can't just embed every disk. What you really need is a friend. So you also need a G, which is some S2, also mapping in to M4, such that three things. The first is that the algebraic intersection between F and G is 1. So let me draw what I mean by this. So the blue thing is meant to be G. This condition, this lambda, that's a new symbol. By this I mean count up all the intersections between F and G. These all have signs. These signs are supposed to add up to 1, plus or minus 1, but let's just say 1. Change the orientation of G if you need to. So that's what that lambda is supposed to mean. Okay, all right. The second condition is that the algebraic self-intersection of G is 0. And that means if I count up all the self-intersections of G by sign, well, those should also add up to 0. That's why I drew it like that. Finally, there's one last condition, and it's that G has a trivial normal bundle. So you're used to thinking about normal bundles. I mean like a thickening of G into a neighborhood. This means that it looks like S2 cross D2. You should be a bit annoyed with me because that's not an embedding, and maybe you're not used to thinking about normal bundles of embeddings. And that's part of why I said the word immersion there, so you can define normal bundles for immersions in a smooth setting, because the tangent bundle sits injectively. So, just in case that's confusing, you should just think about this as push-offs behave nicely for G. And you should be also a bit annoyed with me about like, oh, it sounds like I'm using all these words for smooth manifolds. Turns out it does make sense topologically. But that's a long story that I don't want to talk about. But if you're uncomfortable, just imagine M is smooth, oriented, things like that. But I promise it makes sense more generally. So this is my input into the disk embedding theorem. The output is going to be, well, an embedding. So I'm going to be able to replace my F with an F bar, and my G is not going to become an embedding, but this algebraic intersection was 1. I'm going to get something with geometric intersection 1. So this is a sort of try to replace algebra by geometry kind of thing. I get to replace this map of a disk into an embedding, and then this algebraic intersection, this becomes a geometric intersection. So the outcome is the following. F is homotopic to F bar. This is regular homotopy Rao boundary. G is homotopic to G bar, such that F bar is a locally flat embedding, and G bar is what we say geometrically dual to F bar, meaning by definition that F bar intersect G bar is a single point. Okay. very early in the morning to see the disk embedding theorem for the first time. I don't know, for many of you perhaps this is the first time. Does the statement make sense? Hopefully the picture is helpful. What I would really like is to be able to just have an immersed disk F, so any map of a disk into a Four manifold, and then just upgrade it to an embedding. It turns out I can't do that. But once I have this friend G satisfying these properties, then I get to do that upgrade.
So can you recall what we assume about F?
This is all we assume about F. So I am assuming that on the boundary it's an actual locally flat embedding. That's part of what I meant. That is what I meant when I said relative to the boundary. Like the boundary info did not change. So tried very hard to match it up. I don't know if I succeeded. So on the boundary it stays fixed. Regular homotopy means homotopy through immersions, usually in the smooth category, in the smooth setting. Topologically, it means it's a sequence of isotopies and Whitney moves and finger moves, if that means something to you. But you should ignore this if you haven't thought about that. So I just mean that I can keep the same boundary information, but have an embedding. This, you could start off with a smooth Four manifold, in which case any continuous map can be perturbed to become an immersion, perturbed to become generic, and have these transverse double points. So that could be your input if you wanted. The reason I wanted to specify, side note, the reason I wanted to specify an immersion rather than a continuous map is because I wanted to use the word regular here. And that's helpful for things to be correct on the boundary for framing reasons. If you're OK to not think about framing reasons for now, just think of that as a continuous map. Okay? Does that help? Is that? Okay. So if you don't care about framings, which if you're seeing this for the first time, don't care about framings, just think of this as any continuous map, which is an embedding on the boundary. Yes?
Can I understand this version business and say any continuous map can be perturbed so that there are only finite many points of self-intersection?
That's right.
Each point of self-intersection, it looks like
This.
like an intersection of, topologically, after homomorphism, it looks like intersection of two planes in R4.
Mm-hmm. That's right. So maybe, again, if you're seeing this for the first time, imagine M is smooth, OK? But if you're, I don't know, if you're interested, in the smooth setting, you all saw in your very first encounter with differential topology that the space of immersions is open and dense in the space of continuous maps, something, something, something. And that's like something that one might learn in first semester differential topology. I never took first semester differential, so maybe if you didn't, you're not alone. But it's sort of the sort of thing that occurs in a first semester differential topology class. But you can ask this question in the topological setting. Suppose I have any old continuous map into a topological Four manifold. Claim you can homotope it so that it looks like a locally flat embedding except for finitely many transverse double points. This turns out to be true, but it turns out to be much, much harder to prove. By the way, yesterday I told you the very powerful theorem of Quinn, which said that Four manifolds are smooth away from points. So one way to prove this result would be to, you have your map. As long as it misses a point, remove that point, use the smooth result, put the point back in. But the version of this theorem with the smooth input is what you need to prove Quinn's result. And then you need Quinn's result to prove this theorem with the topological thing in the beginning. It's too early in the morning for this. But the history is that you first prove it with smooth Four manifolds, simply connected. Prove that theorem, still with the locally flat embedding. Then you use the smooth to top version. You take that result. Quinn takes it and proves all sorts of amazing four-manifold results. And then using those amazing results, you finally get to prove the top-to-top version, which I've written here. But we are all very lucky. We don't need to look into these proofs. We just get to appreciate this result and use it. Okay? So knowing the history is fun. Is it? Knowing the history is allowed, but we don't have to worry about it, is the point. That's a long answer to your not question, but.
Can I ask one more
Yes.
question? So in order to understand the meaning of this, suppose M is just a four-ball.
Yes.
And if say some the not of the solid yesterday, some one to the not KS3, and I take this cone construction, that gives me a disk.
That's right.
Which I guess is already immersed. I mean,
Sure.
it has no double points.
So
in this case, what does the theorem say? It says there is no G, or?
So there are two answers to this. The first is that an immersion, that is not a generic immersion. So a generic immersion should be a locally flat embedding, except for transverse double points, or smooth embedding other than transverse double points. And in that cone point, it's not locally flat nor smooth.
No, yeah.
Right? So that's why that.
But I could make this.
But you could make it. Okay.
I mean, you seem to be saying I can just start with any F. Generic. So the question is, what happens if I F is made by its own construction?
Can I interpret your question as, what about M equal to B4? And the first answer I wanted to give you, because as a knot theorist, the first thing that I want to do is slice knots. And so you want to sort of take this theorem and apply it to slice knots. But, okay, we will see later how to apply it to slice knots.
No, I want to apply it to a non-slice knot. See why I'm not fail.
I agree. But I want to tell you why you can't apply this directly to B4. Do you see why? Like, you can't just take, why can't I find a knot in S3 bounding a disk in B4 with this sphere G? Can I do that? Does there exist such a thing? Yeah? That's exactly right. That's exactly right. So notice that one of the things I needed here is this algebraic intersection is 1. And that is a homological intersection, right? And B4 doesn't have any intersection form. It has no homology. So I can't possibly find a dual sphere, G. I can't possibly find a G for my F. So you could take every knot in S3 bound some immersed disk inside of B4. For example, the cone. But I could not ever find a G that intersects that disk algebraically once, because then both classes would have to be sufficiently non-trivial in homology, and that's just not possible. Does that make sense? Okay, so you could always take in S3 a knot. Gregor wants me to take the cone, but you don't even have to take the cone. You can always find an immersed disk like this just by changing the crossings or something like that. So if this were an actual knot and this was B4, I'll never be able to find, we can never find G if this were delta. You'll never find G such that this lambda Fg is equal to 1, because that's a homological intersection. By which I mean this intersection is the one that's dual to the cup product, right? So you all remember the cup product. This is just the homology version of the cup product. And B4, S4, they just don't have that, because there's no H2. And then Grigor had the other point of like, what if I started off with the cone? So I could just take that picture. So I could take the cone. I mean, that already looks like an embedding, but that is not. So this thing, I mean, it is like a embedding in the point set topology sense. But it's not locally flat, as we discussed. I mean, part of what I was saying about these generic immersions is that they are locally flat embedded everywhere except precisely at these points, at these double points. So you could apply the theorem that I was talking about to that disk, and when you do that homotopy, you'll get something like that. It's a very long answer. Is this helping? How are you all doing? It's like good, bad, happy, sad? Yes? That's right. Mm-hmm. So I mean, there are spheres in B4. They'll just always intersect algebraically trivially. Okay. So on the very first day, I was saying things about why are we interested in studying surfaces in four manifolds. I didn't tell you very much about this theorem, but there's a reason this is my favorite theorem about surfaces in four manifolds. I'm not going to go too much into the applications, although you heard a little bit about it a moment ago when I said that that big Quinn result that I keep talking about, that depends on this result, like the baby version of this result. I mean, but the baby version of this result, you also use it to prove things like the topological four-dimensional Poincare conjecture, not a baby corollary. So that's a really big deal. We use it to prove things like the H-cobordism theorem. I guess I should point out that Mike Freedman proved this result and then received a Fields Medal for it. So it's a really big deal, is what I'm trying to convey. I will not use it. I will not prove it, because that will take a million years. But I want to apply it to prove something today. That was my plan. So let me state a couple of things, and then we'll prove one of them. Okay. What should I do? I should do this. The theorem that I wanted to prove is the following. Yes? That's a great question. So the question was about uniqueness of F bar. There is no uniqueness in this theorem. You could ask about things like uniqueness of slice disks and whatnot, which is what we'll use this theorem to, what we'll apply this theorem to. And in some of them, you have uniqueness results, but not all of them. So you have to apply some conditions. I would guess that this F bar is not unique, but that's just not something I've thought about before. It's a good question. I should say that most of the time when we apply this theorem, it happens like in like the middle of a proof, if that makes sense. And when we consider uniqueness questions, it's usually for the entire thing that we're constructing. So that's why I'm not completely sure about that. I should think about that more. Certainly in the proof, you don't see any sort of uniqueness. I'm wondering, let me stop there. All right, so I spent some time telling you why you can't apply the disk embedding theorem to slice knots in B4. And now I'm going to tell you you can use it to slice knots in B4, because there's the following theorem of Freedman and Quinn. which says that if you have a not in S3, if the Alexander polynomial of your knot is 1, and remember we defined the Alexander polynomial yesterday in terms of the Seifert matrix, then your knot is topologically size. You may have seen this result before. I mentioned it on the first day. It has a number of proofs. One method of proof is to use the disk embedding theorem to prove something called the surgery sequence is exact and do a very indirect proof of this. That was, in some sense, the first proof of this. But the proof that I want to give you is a different, more constructive argument where you get to apply the disk embedding theorem directly, just because I thought it's easier to understand and a lot more direct and visual. So the proof that I want to give you is due to Garofalidis and Teichner. Basically, the idea is that I'll sketch for you this proof, and then we'll take a break. As I said, there is a problem about applying this theorem to before for this homological reason, and therefore we'll need a generalization of this. So that will have to do with this fundamental group condition. So I won't apply it to a simply connected four manifold. I'd rather apply it to a four manifold with fundamental group Z. I didn't tell you about these generalizations yet. Turns out that this theorem applies in lots and lots of different four manifolds for different fundamental groups. In particular, finite groups, abelian groups, solvable groups, groups of sub-exponential growth, all sorts of groups. Basically, every group that you can think of, this works, except for non-abelian free groups. And this is, in my mind, one of the big open questions about topological four manifolds or just four manifolds in general, whether you could just say arbitrary fundamental group here. Okay? But Z is abelian, and therefore I do get to apply it here. Okay. The rest of the theorem is the same. Anyone going to object? Yeah?
Some condition about intersection with coefficients.
Exactly. Thank you. So the rest of it is the same in some sense. I said here that these intersections are just the signed counts of, like, you take all of the points of intersection, and then you just add up the signs. But when you have a non-trivial fundamental group, you have to use something called the equivariant versions of these. This means that for each double point, you not only have the sign, but you also have some element of the fundamental group. This will not be important for us, so I'm just not going to tell you about it. But you should just know that there's some more general intersection thing that you have to consider. But the proof will be sketchy enough that this will not matter. Okay? But the rest of it is the same. Is that okay? Will you let me get away with that? Okay. Great. Thanks. So, I'll tell you why the Z is the important case once we get to it. I said I'd give you this proof, but in fact, I'll give you an even sketchier proof. I'll give you the one for the Whitehead double of a knot. And let me remind you slash explain what the Whitehead double even is. So the Whitehead double has the following picture. Suppose I have a knot like the figure 8 knot. In order to build the Whitehead double, the first thing I'll do is I'll take the linking number 0 parallel of it. So now I have two copies of the Whitehead double that have linking number 0 with each other. And I'm going to delete a little part and then add in a little clasp. Schematically, if this is your knot J, the box just means that's where all the knotted stuff is happening. The Whitehead double looks like this. Where two strands going through a box means that there's a linking number 0 pair of strands being tied into J. I'm being clever, and that's why I drew the figure 8 here. If I had drawn, let's say, the trefoil, not my favorite knot, we agreed yesterday, then the parallel wouldn't have looked quite so nice. They would have had to look a bit more twisted because of the writhe. Okay. If you know these words, that will make sense. If you don't, ignore it. There was a question on the first day about positive versus negative Whitehead doubles. Positive means it's this clasp, and negative means it's this clasp. So this is what I would call Whitehead plus of J, and this is what I would call minus. To us, topological four-manifold people, there's no difference between the two of them. Like, obviously, they're different knots, but all our results will apply equally to both of them. Smooth people care a lot about these signs of clasps and so forth. So for example, smooth people can tell you that the positive Whitehead double of the right-handed trefoil is not slice, but they could not tell you at the moment if the negative Whitehead double of the right-handed trefoil is smoothly sliced. So let me, note this was first done by unpublished independent work of Kassin and Akbulut, that the positive Whitehead double of the right-handed trefoil is not smoothly sliced. And it's completely open whether minus Whitehead double of the right-handed trefoil smoothly sliced, or either Whitehead double of the figure 8 knot. So this knot, smoothly, we have no idea. But topologically, all of these things, except that one, all of these Whitehead doubles are topologically sliced because all of them happen to have trivial Alexander polynomial, which is easy to compute, and you're welcome to do it. What will help you in doing that is the following fact. That there's a very obvious Seifert surface for the Whitehead doubles, namely, you're kind of looking at it. There's this flat annulus, and then there's this little twisted bridge that goes above like this. Some people see this, some people don't. So you could redraw it like that. No, that's the one I want. So that's another picture of a Whitehead double. I have no idea which one, okay? It's one of these clasps. I think it's this one, but I don't actually. But it's one of them. So this is another picture of the Whitehead double, plus or minus, who knows. And then you can very easily write down the Seifert matrix. What's important is that this curve that's going along this band has self-linking 0 because that's what that box meant. So in the Seifert matrix, you'll get a 0 over there in the corner. Okay. That seem reasonable? I'll just work with that one. Like the proof will apply for other cases. It's just a bit more technical. Let me. Oh, right. To do your Seifert matrix computation, you'll probably want to use these core bands like we did yesterday. But in fact, I want a slightly different basis. So I claim that there's a Seifert matrix that looks like this. And I'll in fact use this basis instead, because that makes the matrix look nice. But anyway, doesn't super matter. Let's call this A and B. And then here were A and B, A plus and B plus. So there's some basis which is particularly nice. Anyway, this is not the important part. With that lead up, we can finally get to the sketch of the proof. Okay. This is my Seifert surface F. So the overall strategy is the following. I have my knot, Whitehead of J, or more generally any Alexander polynomial 1 knot, and it's the boundary of some Seifert surface. It's a genus 1 Seifert surface, which is especially nice. What I'll do is I'll find some homologically essential circle. Let me check that I'm doing the right one. A. Yeah, it will turn out to be this red one that goes in the weird way, but schematically, it looks like that. So some homologically essential circle on this Seifert surface F. And what I'll do is I'll find, I want to find a disk for this Whitehead of J, but instead I'll find a disk for this red curve in the complement of F. Okay? So I'll find some disk bounded by this J away from F. It will be like this, that's why I drew it like this, but in your mind, in the best possible situation, it would be that disk. And the reason I like this is if I could find such an embedded disk, then I could cut my, well, maybe I could put it here. If I could find such a disk, then I could cut my Seifert surface along that red circle and then glue in 2 copies of that disk. 2 parallel copies. These are actually disks, right? So when I cut open my Seifert surface, I created these 2 new boundary components. And then I plugged in those 2 new boundary components by 2 embedded disks. Those disks were sort of far away. They were only glued along the boundary. And therefore, I have sliced my original knot wide head of J. Okay? Does that make sense? This is sometimes called doing surgery on the, surgery is like an overused term, sorry. But this is, you're doing surgery, you're surgering this surface F along this red circle. That's a term you may have heard of. Okay. That's right. So if this were some delta, this would be delta and overused symbol delta plus. You do have to be careful about some things. For example, you want to make sure that like this push-off, there's some framing things to keep track of. But because we're being sketchy, we're not going to today. But you must in real life. And that's where those words like regular, homotopy, and so forth are there to help you. Okay. Strategy makes sense? Yes? Yes, that's exactly right. So if you have another genus over here, then you'd have another red circle. And then now you are looking at a link, and you're trying to find disks like this. You want those disks to also, of course, be disjoint from one another. So in general, slicing, I've been talking about slicing knots, but you may as well be slicing links. This sort of slicing when you have disjoint disks is called strongly slicing sometimes, or just slicing because that's what it should be. But that's absolutely right. If you had a many-genus surface, you're just looking for a many-component link that you might be able to slice in the complement of your surface. Disjoint slice disks do the same procedure. I won't draw it here, but you can do it. Other questions? Yes? We're getting to it. We're going to use the disk embedding theorem. This is not easy, and it's not always possible. But we haven't talked about how to do that yet. Okay. Other questions? All right, so how do we do this? And where does this pi1z come in? Well, the pi1z comes in the following way. So I have this ciphered surface F, and I'm going to take this ciphered surface F from S3 and push its interior into B4. Okay? That thing I will call F plus. Maybe it should be minus because it's like pushing down into B4. Does that make sense? To just push the interior into B4 like that? So it would be like, if this entire thing were in S3, I'm just pushing this surface to now lie inside, but the knot will stay in the S3 bit. Or if you wish, you can keep this where it is and then just attach an external collar and like put a little annulus on top of the knot. Okay, but so step one, push the interior of F into B4. Then there's a bit of a black box if you haven't seen this before. You have to note that pi1 of B4 minus this new F, this is in fact Z. If you have seen these things before, when you push your surface in, you're creating just a single minimum. And like all of the pi1 of the complement comes from those minima. Like you can do a handle decomposition. It's not hard. So easy fact if you know all the background. It's a weird meaning of easy. Okay. Yes. Thank you. So F plus is the thing where I've pushed the interior in. And then the complement of that has infinite cyclic pi1. And this is great because that's where I'm going to apply my disk embedding theorem. I know I can do that. And I want my disks to lie in the complement of the surface anyway. And so like I'm finally like, hey, great, I'm now able to use the disk embedding theorem, which I couldn't do in before. So this strategy of sort of pushing your problem one step further actually works. Has a chance of working, and we will see in a moment that it does work. Yep.
This is slow. We are not saying that F is a disk. We say it's always a disk, even if F is a.
That's right. And again, it really is the fact. That's fine. So regardless of its genus, if you start with a ciphered surface inside of S3, and you push its interior down into B4, the complement will have pi1z. And for Handel diagram Morse theory people, it's because it has a single minimum. So for example, if you were drawing a Handel diagram of its complement, it will have a single one handle. And so it kind of can't, it has to be cyclic, and for homological reasons, it has to be Z. If you don't know those words, ignore them. Okay. How are we doing? Reasonable? Strategy makes sense? We've pushed the ciphered surface in, and now I just need to find these disks in the complement. I'm going to use the disk embedding theorem, big surprise. So once I need to find some immersed disk with a friend, and then I'll just apply the disk embedding theorem to get embedded disks. We agreed I won't talk about framings, so let's not. So right now, all I need to do for you is to find the input of this theorem, f and g, little f and little g, so that little f kind of looks like this, except it's immersed. And that's going to be relatively straightforward. Again, I'm going to skip a lot of details. But notice, like these circles A and B, these circles in S3, well, they bound immersed disks in B4. For example, you could take a cone and then use your facts about smooth maps if you wanted. Or you could, whatever these circles are, they are tied into the knot J, but every knot J can be unknotted by crossing changes. And if you look at the track of that crossing change homotopy, you get an immersed disk. Okay? So fact, every knot bounds an immersed disk inside of B4. And therefore, in particular, A and B do as well. So notice, so step 2, little a and little b. If you're being careful, maybe you should think about little a plus and little b plus that are on F plus. I will not be that careful. These bound immersed disks. Big A and big B inside of B4. And because I only pushed F plus like radially downwards, they bounded in the complement of F. So there are some pluses missing, but let's not worry about them. Okay. All I need to think about is A. So the big A is an immersed disk that looks like this with the right boundary, except it's immersed. Okay. So step 3, this is the most technical part. Feel free to zone out if you'd like. So we need to use B to build like that G. So the big A is going to play the role of F. And I need something to play the role of G. So that thing is called algebraic dual. For big A. Okay, this will be a bit weird. Sorry. What you'll do is you look at B. So again, ignore this if you'd like. So this one was A. schematically. And then this one is B. But now, because I've pushed it into B4, that's a circle living in a 4-dimensional space. So it has a cross S1 inside that space. So that's B now lives inside of B4. So it has a tubular neighborhood, which is B cross D3. And so there I can find a B cross S1 that kind of hugs my surface F. This is called the rim torus. Another way to think about it is that this surface, once you've pushed it into B4, has a D2 neighborhood. And the boundary of that D2 gives you, each of those D2 fibers has a boundary S1, which is called the meridian of that surface. And for each point on this circle, I'm going to take the meridian. So I'm going to get a torus that sort of hugs the surface as it goes around. It's a meridian. It doesn't touch the surface. It's just sort of there. In this picture, you might imagine taking the point that's directly above and below and like floating around like that. That looks like an S0, not an S1. But because we're actually in dimension 4, you really have an S1, not an S0. Okay, that was very confusing. In this picture, you see a B cross S0 in the complement of F. And I'm telling you that because we're in dimension 4, you actually have a B cross S1. Okay? So there's something called the rim torus. So this is step 3 still. Use the rim torus. B cross S1 living in the complement of this surface. Just little b, actually little b. Actual little b, we haven't used it yet. We're working on it. Yes. Spoiler. You will need big B for that. But spoiler. But yeah, that's exactly right. So the first thing you have, okay. This is pretty sketchy, okay? So I'm not going to give you full details, but let's talk about it later if you'd like. Because of that number 1, that rim torus intersect that big A is precisely 1, lambda, sorry. So this torus satisfies that lambda condition, because I'm looking for a G to satisfy all of the G conditions. So the first G condition is satisfied by that rim torus. But it's a torus, not a sphere. I really wanted a sphere. And this is where JB's idea comes in. Well, that B cross S1 has longitudes B, and you can use copies of big B to serger the rim torus into a sphere. What does sergering mean? It means that, except now you're doing it to a long circle rather than a short circle. So serger B cross S1 using copies of B. Oh, so this is because linking number of A and B plus is 1. You serger this using copies of B to get a sphere. Just an immersed sphere. Let's still call it G. You have to convince yourself that the other properties still hold. The other I just mean 2 copies because I used 2 copies. But if you prefer, it should just be 1. It depends if that is 1 or 2.
This is a nice torus, right?
Yes. Two just meant, am I using this disk once or twice? And it's just one genus surface. So I only cut along one curve. But now I get two boundary components, so I put in two copies of B. No worries. Okay, almost done. Great. First condition was true. This is still true. This is still true. Why is that? Well, because I used two copies of B with opposite orientations. So in terms of signs, it's still the same, because whatever new thing I created got killed by the other copy, since used two copies of B with opposite orientation. You should still complain a little bit about, I told you that that is the equivariant intersection number, not the signed intersection, not the only signed intersection number. But because this number is 0, that's why even the equivariant intersection number vanishes. Okay. Let me just leave it at that. Happy to tell you more about this later. But roughly the point is that once you know how to do, once you take this rim torus, do this surgery, create this algebraic dual sphere G, I promise you it is actually an algebraic dual sphere lying in the complement. Apply your disk embedding theorem, acquire your embedded disks, serger your original Seifert surface, produce your slice disk, and then you win. All right. Questions about this proof? I know that was complicated. Try to avoid thinking about step 3. But does the overall idea make sense? Judson. Yes.
So if I wanted to do this development arbitrary, would I need to be worried about disjoint inverse disks and disjoint dual spheres? I should be able to disjoint this.
That's a great question. So the question was, how do I address the case of more genus? I know I wrote disk embedding theorem, but actually it's disks embedding theorem. And the point is that there is a version of this for finitely many disks. Each of those disks will need a friend. So you'll have F1 through Fn, and then G1 through Gn. And it turns out that those don't need to be disjoint. They just need to algebraically look disjoint. So your original, the Fs can intersect arbitrarily. The Gs, well, they get to intersect one another as well, but they just have to be algebraically canceling. And because we use this rim torus surgery method, we're always the rim tori are disjoint, no intersections there. And all the extra intersections will come from this two copies of the disk B. But because it's two copies opposite orientation, plus this other fact, you always get them to be algebraically canceling. But you can see this is why I didn't do the higher genus surface, higher genus version, because it's unnecessary. Well, okay. There are more complications that one has to address, but the basic idea of the proof is still this. So the main thing you've already encountered, and then in the higher genus thing, you have to deal with some technicalities that are not that interesting. But it all still works. The Garfalidis Teichner paper is really nice, so I can highly recommend reading that one. Okay. I want to tell you one last thing before I finish the existence section, and then we can move on. We can have a short break. So one of the things I really like about this construction is that the condition is so simple. All you have to check is this very algebraic condition of Alexander polynomial 1, and then you get this cool topological output. And in general, in the topological setting, this is a theme. And you'll see more of this when we talk about uniqueness as well. So topological results are kind of annoying to prove sometimes because the tools you're used to having are just not there. So you have to sort of, I don't know, be really frustrated and or clever, one of those things. But when they work, like they give you some really powerful results and things that the hypotheses tend not to be that complicated. And I'll tell you more about this in the uniqueness section. But just like I couldn't bear not to tell you about this, I can't bear not to tell you my favorite existence open question, which is still open question, which is the following. Well, one thing that you've noticed in this entire existence section is that there is this big discrepancy between smooth embeddings and topological embeddings, by which I mean locally flat embeddings. Okay? And in particular, you noted that not all locally flat embeddings are smoothable. Like we saw examples in CP2, where there are homology classes that are represented by locally flat embeddings, but no smooth, like a smooth embedding would have to be higher genus. And therefore, these are locally flat embeddings that cannot be smoothed. But we have no such example in S4. So here is my favorite open question. Does there exist a locally flat surface embedded in S4, which is not smoothable? And we know nothing about this at all, which is wild to me. These examples, we constructed locally flat sliced disks inside of B4. And for example, if you start off with a not smoothly sliced knot, those disks are not isotopic to smooth disks REL boundary. So we have REL boundary examples in B4. And we have examples in other 4 manifolds. But when it comes to S4, we have nothing. We have examples in S5. So there are S3s in S5 that are not smoothable. That's a result of Lashoff from the 70s. But I didn't know that this was open until very recently. And this is part of why I think it's just very surprising to me that that is still open. And as we talk about uniqueness results, maybe you can think about why this is so difficult. Okay, that first part was going to take like 20 minutes, and then we were going to have so much time to talk about uniqueness. It's funny how these things work out. Uniqueness, what do I mean by that? Let me start off with a definition that's not surprising at all. Suppose you have 2 surfaces, K1 and K2, some surfaces sitting inside of M4. These are ambient isotopic. If there exists an ambient isotopy, namely some big phi going from m cross 0, 1 to m, such that each phi t is either homeo or diffeo, depending on whether m is smooth or topological. I'm going to write down diffeo. But of course, there's a version with homeo, such that further, phi 0 is the identity, and K2 composed with, phi 1 composed with K1 is equal to K2. If you have done like classical knot theory, you've seen this. I've just replaced some dimensions from ones. Dimensions have been pushed up a little bit. I just wanted, for folks who are not traditionally or usually working in knot theory, just to see this definition for the first time, for at least once. I mean, what this means is that you can somehow deform your ambient space so that one surface is mapped over to the other one. And because of the isotopy extension theorem, this thing that I have written right now is the same as there's a one-parameter family of embeddings taking one of your embeddings to the other one. Okay? So those two are the same as long as your surfaces have sufficiently nice normal bundles, which they do. This is what I mean by uniqueness for now. It's like, as in classical knot theory, we'll consider two surfaces to be the same if they are ambient isotopic. And again, if you are used to or have seen classical knot theory, this should not surprise you at all. Similarly, it will not surprise you that there's some notion of unknottedness. It's a little bit more confusing because usually in classical knot theory, unknotted would mean it's the boundary of a disk. But now you don't just have circles or spheres, you have higher genus surfaces as well. And so we say that a surface inside M4 is topologically or smoothly unknotted if it is the boundary, if it bounds a smooth, top came first, a topologically or smoothly embedded handle body inside of M4. So let me specify. So if your closed orientable surface had genus G, so this needs to bound an embedded handle body HG, by which I mean the boundary connected sum of G S1 cross D2s. I mean, these are the things that Powell has been talking about, right? Like the actual handle bodies that you're used to thinking about inside of M4. So HG is, of course, this guy, the three-dimensional filled in, that guy. I've tried very hard not to use too many adjectives, but here I used the orientability adjective. In the non-orientable setting, well, like if you have a Mobius, if you have an RP2, it's not the boundary of a three-manifold. So you have to like think about what it should mean for that to be unknotted. There are ways to address that, but for lack of time, let me not talk about non-orientable things, but people do think about it. And I'll mention it briefly later as well. But perhaps this definition should also not surprise anyone. Certainly for the S2 case, all I'm asking is, as before, if I have an embedded S2 in my four-manifold, is it the boundary of an embedded B3? Right. That's my usual definition of unknotted. There's an obvious question that one can ask. So recall, / here is a fact from classical knot theory. Suppose you have little k a one knot. This is unknotted if and only if the pi1 of the complement is Z. So an obvious question you might ask is, well, what about the four-dimensional analog? Question makes sense. So here you have the topological 4D knotting conjecture. Suppose you have a locally flat surface with infinite cyclic pi1 of the complement. The conjecture is that this is unknotted, topologically unknotted. And that's true. The following cases. So let's say this is sigma g. So, well, let me. So sigma, this is true for sigma equal to S2 by Freedman and Quinn. I'm hoping to outline that proof. We'll see. We'll see what the future holds. So perhaps you might think, like, why do we care about higher genus? We should just stop at 2 knots. And so at least for 2 knots, the topological thing is actually true, which is pretty cool. It's certainly, but before I knew it, I would not have expected it. And it's true for sigma orientable and genus bigger than or equal to 3 by Conway and Powell. From 23. The G equal to 1 and 2 cases are open. Surprising fact. I made a mistake. If I don't specify that sigma is orientable, like I won't always get Z here, like even homologically. So if sigma is orientable, then H1 is Z. So this is saying pi1 is the simplest possible. But if sigma were non-orientable, you would in fact get H1 is Z mod 2Z. So then pi1 only, like the simplest pi1 is like Z mod 2Z rather than Z. So there's a non-orientable version of this conjecture, and that's also known in certain cases. I don't want to talk about it too much, but there's like recent work in this area. So Conway, Orson, and Powell worked on this in 2023. Mark Pinkovich worked on it in 2024. So like these are very recent results about topological unknotting questions for non-orientable surfaces. My agenda is very clear, right? I want to point out that people are working on this right now. Like there are open questions and there's progress being made this year, maybe even this day, who can say? But like this is like something that people are working on actively. 2023 is super recent. So let's just add the word orientable here. The more general unknotting conjecture will just say this is cyclic, but let's not talk about it. Right. And hey, that's open. The genus equal to 1 or 2 question is just open. Of course, there's a smooth analog. Let me state this one as a question. Suppose you have sigma smooth oriented surface. With pi1 cyclic. Is this unknotted? Smoothly unknotted. And in that case, the orientable question is just completely open. We have no idea. We have nothing. I should point out that just like here, in the non-orientable setting, we have topological unknotting. In the non-orientable setting here, we actually know that it's false. So there exist so-called exotically knotted non-orientable surfaces inside of S4. The first examples of this were by Phoenician, Crick, and Vero back in the 80s, 87. And in fact, just last year, Jin Miyazawa announced that there exists an RP2 sitting inside of S4 that is topologically unknotted but not smoothly unknotted. So the non-orientable smooth question is actually settled. And the orientable smooth question is just completely open. And we have just no idea whatsoever. More generally, we can ask the following question, which we also don't have. It's just completely open. So more general. Does there exist any pair of surfaces in S4, orientable, I did not. I was trying not to talk about it too much. So for an unknotted, for RP2s inside of S4, so connected sums of RP2s inside of S4, there is this additional complexity that comes from the Euler number of the normal bundle. So if you're an orientable surface in S4, your Euler number is 0 because there's no intersection form in S4, as you know. But if you have a non-orientable surface, well, that's something that's in like Z2 homology. So it only gets to care about Z2 Poincare duality things. So it potentially has even Euler number within a certain range. And all of those can be realized. So to answer Gregor's question, let me do this over here. Oh no. Here, it doesn't bound something, but I'm giving you two standard embeddings. This is what I'm trying to say. So you could take this Mobius strip in S3, push it to one side, and cap off the unknot with a disk. Or you could take this Mobius strip in S3, push the interior into B4, and cap off with an unknotted disk. These will have two different Euler numbers. And these are both model unknotted RP2s inside of S4. And so if you have your preferred RP2, it will have some Euler number. And depending on that Euler number, being unknotted means being isotopic to either this one or that one. And Euler number is preserved under isotopy, so it can't be to both. So in the non-orientable setting, what we usually do is we specify the model unknots. So for RP2s, I've described the two model unknots. And for a connected sum of RP2s, you get connected sums of these. You get to mix up which ones you take. So for Klein bottles, you have 3 different ones, something like that. And for every H, you get more and more model unknots. And then, therefore, in the topological non-orientable unknotting conjectures, you not only have the non-orientable genus, but also the Euler number as something you have to control. There's a long story that I don't want to get into any more than I've already done. But can we talk about this later? Okay. Okay. More generally, there's this open question of does there exist any pair of closed orientable surfaces in S4 that are exotically knotted, meaning that are topologically isotopic, but not smoothly ambient isotopic. That's totally open, and we have no idea. I am totally over time, so let me end by mentioning the following. There are examples in other four manifolds. The first ones of these were due to Finchel and Stern. Using something called rim surgery. It's related to the rim torus that we saw earlier. There also exist examples with boundary. Even in B4 of exotic disks. I'm so late. Let me not say more about this. Let's start off on Friday by talking more about this. There's a whole industry of people working on exotic surfaces inside of interesting four manifolds. For example, here you have work of Kyle Hayden in using Kavanagh homology. You have work of Juhas, Maggie Miller, and Ian Zemke using more Hegard-Flohr things. All sorts of smooth things that you know of can be used to address these questions. The point I want to make is that they don't work in S4. So even though we are very good at finding exotic surfaces, and there's a whole industry of it, you really need something interesting either going on in the topology of the four manifold, or you need something interesting going on in the boundary, because that's somehow where our invariants are going to come from. But when you're looking at closed orientable surfaces sitting inside of S4, you have neither of them, and so we're kind of stuck. So this is kind of like a challenge to smooth people in the audience that this is a relatively very easily stated question, very natural question, but we really have no idea how to do any of this. Okay. Friday, I'll start off by describing what rim surgery is. It's a nice straightforward operation. And then maybe I'll talk about the topological and knotting thing for S2. Instead of talking about other things, probably we'll just end with some sort of summary so that it's like a calm and relaxed ending rather than a frantic one. But if you have requests or suggestions for what should happen on Friday, let me know. Thank you for your patience. See you on Friday.